The idea sounds impossible. Light, the fastest thing in the universe, frozen, stopped, motionless, as if time itself pressed pause on a photon. But it's real, and it's not science fiction. For decades, physicists have been taming the wild speed of light, and now they can freeze it completely. This mind-bending breakthrough doesn't just rewrite the laws of physics textbooks, it opens doors to revolutionary technologies, from quantum computers to unhackable communication. The journey begins in 1999. At Harvard University and the Roland Institute for Science, physicist Lin Hao and her team achieved the unthinkable. Inside a small laboratory, using a cloud of ultra-cold sodium atoms chilled to near absolute zero, the speed of light was reduced from 299,790 kilometers per second to just 17 meters per second. That's about the speed of a bicycle. But the story doesn't end with slowing light. In 2001, the same team did something even more astonishing. They stopped light completely, using a state of matter known as a Bose-Einstein Condensate, a strange quantum state where particles behave as a single quantum entity. Light pulses were halted, stored, and later released without losing information. To grasp this, imagine sending a message through a fiber optic cable. Now, picture that message being captured, frozen mid-transit, stored safely, and released at will, all without distortion. That's the core of what stopping light enables. But how is this possible? Light is an electromagnetic wave, constantly in motion. Freezing it requires manipulating the very medium it travels through. Bose-Einstein condensates provide that control. When atoms are cooled to temperatures a fraction above absolute zero, they form a unified quantum state, effectively a superatom with remarkable properties. In this bizarre state, the usual rules of light propagation change. Through a process called electromagnetically induced transparency, or EIT, an opaque material can be made transparent to specific light pulses. The incoming light pulse slows dramatically, its energy and information transferred to the atomic cloud. The light itself ceases to exist as a traveling wave. It's stored as a quantum imprint within the atoms. Later, with a secondary control beam, the light pulse is revived, continuing its journey as if nothing happened. This isn't just a laboratory curiosity. The ability to freeze and store light has profound technological implications. One of the most promising is in quantum memory. Quantum computers rely on fragile quantum bits, qubits, which need to be stored, transmitted, and manipulated without losing coherence. Stopping light offers a way to temporarily store quantum information, acting as a reliable memory buffer for quantum networks. Another application is in ultra-secure communication. Quantum information carried by light can, in theory, be paused and stored, making eavesdropping or interception nearly impossible. Entire communication networks could become fundamentally unhackable. There's more. Optical switches that rely on controlling light speed or freezing light pulses could revolutionize data processing, making future computers dramatically faster and more energy efficient. But the implications extend beyond engineering. Stopping light forces a rethink of the very nature of space, time, and energy. Light defines the cosmic speed limit. It shapes the structure of causality, the relationship between cause and effect. Halting light, even locally, reveals just how malleable the universe can be under the right conditions. Over the past 2 decades, advances have pushed this research further. Scientists have frozen light in optical fibers, solid-state materials, and even photonic crystals, structures designed to manipulate light at the nanoscale. Each method brings the world closer to integrating this phenomenon into everyday technology. It all raises profound questions. If light can be stopped, what happens to information traveling with it? Can light be frozen indefinitely? Could entire photonic circuits one day pause, process, and restart information at the speed of thought? What's clear is the ability to control light, not just its direction or intensity, but its very motion, marks a turning point. A shift that could reshape how information, communication, and computation unfold in the decades ahead. The frozen light revolution has already begun. Its ripples will be felt everywhere, from physics labs to the heart of future technologies. And the world is only beginning to grasp the possibilities. Like, share, and subscribe for more deep dives into the strange, fascinating frontiers of science and technology.